Okay, today we're talking about Chapter 4, Section 3, the multiplication of polynomials. Alright, so starting here. The properties of exponents can be used to simplify many algebraic expressions, including the multiplication of monomials. Right, monomials again being 1. Uh, to multiply monomials, first use the associative property and commutative properties of multiplication to group coefficients and like bases. Then simplify the results by using the properties of exponents. Okay, so I know all those words mean little to you, right? I won't say little to you, but kind of, it's very wordy, right? So let's just do an example instead. So multiply the monomials. So what we're going to do here is we're going to begin by simply just mushing it together. We're going to be combining, or we're going to be multiplying the like terms essentially, right? So what I mean by that is the 3 and 5, they're both constants. So 3 times 5 is 15. All right, x squared times x cubed. We know from our exponent rules that we can just all we simply do is add the exponents together when we're multiplying them, right? X squared times x cubed. Well, that's x to the fifth. And then y7 times y is 7 plus 1 is y to the eighth. I wonder if I can fit example 2 on this page. I think I can. Oh, that's a two-parter. No. I'll probably do A on one side and B on the other. Let's try that. So put example 2 over here. Give us a nice little dividing line there. So A, multiply the polynomials. So if you recall in the text it said use associative and commutative properties. True, but we're also going to be using distributive. Okay, I don't think it said anything about distributive properties. So, but we're going to be using distributive property here. And what I mean by that is we're going to take this 5y cubed and we're going to distribute to the first term, to the second term, and then to the third term. Okay, so 5y cubed times 2y squared. Well, 5 times 2 is 10. Y to the third times y squared. That's going to be y to the fifth. 5 times 7 is negative. 5 times a negative 7. Sorry, 5 times negative 7 is going to be a negative 35. And then a y cubed times y is going to be y to the fourth. And then 5y cubed times 6. Well, 5 times 6 is 30, so that's going to be plus 30. And then y just kind of goes along with it. Okay. All right, that's A, and I guess I don't know. B. Well, let's see what happens. Okay, so we have we're going to same procedure. We're going to distribute here, and then we're going to distribute here. Okay, so negative 4 times a positive 2 is going to be a negative 8, and then a cubed times a is going to be a to the fourth, and then b to the 7 times b squared is b to the ninth. That b is low. B to the ninth. And then c times c to the fourth is c to the fifth. All right, and the next term, so negative 4 times a negative 1/2, so that's going to be a negative times negative, so it's going to be a positive. So it's going to be, 4 times 1/2 is 2, so we're going to say plus 2. And then we're going to say the a cubed times a to the fifth is a to the 8, a to the 8th power. And then b to the 7th times b is going to be b to the 8th power. And then the c just kind of goes along with it. And it appears, luckily, we did fit it all in there, so that's good. So, thus far we have illustrated polynomial multiplication involving monomials. Right, that was the first two examples. Next, the distributive property would be used to multiply polynomials with more than one term. Okay, so let me just check real fast. I mean, we did our distributive property. It doesn't say, it just says associative and commutative. Okay, well, we did distribute. We did do our distributive property in examples 2, but whatever. Where are we at? I gotta get rid of that. Next, the distributive property will be used to multiply polynomials with more than one term. For example, and maybe you're familiar with something called the FOIL form. First, outer, inner, last. So what you do basically is you have x plus 3, x plus 5. What you're going to do is you're going to multiply. Okay, this is crazy. I mean, it's not wrong, um, but it is a different way than I'm assuming many of you were taught, right? But let me see if we drop down here to okay, so we do drop down there to example 4. So let's actually do example 4 before we jump into example 3. Okay, and while this is correct and it's true, there's nothing wrong with it. In fact, I rather do like that. But we're not going to do it this way because it's you know what, on second thought I don't like it because we distribute one and then we go back again for the other. Instead, we're going to do the FOIL form, and we're going to start with example 4. But before we do example 4, let's jump to what I mean by FOIL. Okay, now you probably are familiar with it. I remember being introduced to FOIL form when I was in 7th grade, but you know how math is, right? If you don't use it, you lose it. So let's start with, let's see, we'll do it this way. A plus B times, let's do x plus y. I'm not sure if this is even going to help. We're just going to go about it first, okay? So FOIL stands for first. So these are the two first terms, okay? And actually, you know what? Let's actually do this. Let's go all out here. Let's go all out. F O I L. Okay. So the first is my first two terms. Oh, Sherman. My first two terms. I think I did that a second ago too. Okay, so my first two terms are a and x. So we're going to say a x. Okay. My outer are my two outer terms. Right? So we're going to say a times a positive y is going to be plus a y. My inner terms are going to be these two. So we're going to say plus bx. And then my last terms are going to be my two last terms, okay, which is plus ay. All right. Hopefully that helps. I don't know if it will, but at the end of the day, it's very, very colorful, and hopefully it does. But this is essentially the FOIL form, okay? So this is how we multiply two binomials, and we're going to do that a lot. And by a lot, I mean so much in this class and so much in college algebra. And if you take classes beyond college algebra, so much in those courses as well. You're going to be foiling your brains out. So get used to this. So, like I said, let's go ahead and do example 4 first. Okay, so I'm going to rewrite this and make it a little bit larger. 3y plus 2. Just gonna make it a little bit larger so I can really drive home the point of, my FOIL form and putting arrows everywhere. Okay. So the first thing I'm going to do is my first terms, right? 3y and 7y. Well, 3y times 7y is, put this in yellow, is 21y squared. Next up is going to be my outers, so it's going to be these two. So 3y times negative 6 is going to be negative 18y. Oops. Okay. I like to put little serifs on my ones if my ones are large enough, just to kind of differentiate. But anyways, FO and then I, the two inners. So 2 times 7y is 14y, so positive 14y. And then my outers, 2 times a negative 6 is a negative 12. Okay, we're not done there because we have to combine our like terms. So combining like terms, we see that these two are my like terms there, right? So let's put that in green, I guess. These two are my like terms, so I can say 21y squared. Negative 18y plus 14y is going to be a negative 4y minus 12. Okay, and that's multiplying polynomials using FOIL form. Okay, now FOIL is basically just a nice, cute little acronym, but it's at the end of the day, it's the distributive property. Okay, and this particular problem is another example of distributive property, right? The example that we skipped. So it's another example of the distributive property, but there's not a nice, cute little name for it. You just kind of have to go. So here's how we're going to go. We're going to just rewrite this. Okay. So we're going to have to go boom, boom, boom. Actually, let's put the arrows on the bottom part. We're going to have to go boom, 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 and then we have to go boom, boom, boom. Okay. There's going to be 6 terms. It's going to these particular problems get ugly really fast. So let's begin. So starting off, let's put it in yellow right here. 2x squared times 3x squared. So that's going to be 6x to the 4th power. 2x squared times a negative x, so it's going to be a negative 2x cubed. 2x squared times 5 is going to be 10x squared plus 10x squared. And then we start with the 4 here. 4 times 3 is 12, 12x squared. It's going to be plus 12x squared. 4 times a negative x, let's be negative 4x. And then 4 times a 5 is 20, so plus 20. Okay, we need to combine like terms again here. So there's nothing to combine with the x to the 4th, so it's going to be 6x to the 4th cubed. It looks like there's only one cube, so that's good. 2x cubed. X squared, so we have 2x squareds there, so it looks like 10 and 12, so it's going to be plus 22 x squared, and then minus 4x, and then plus 20. That takes up the first degree and the constant. Right? And we just multiplied that. Again, there's not a nice pretty acronym for this particular problem. It's there. We still have to use the distributive property. Interestingly, we actually talk about FOIL at the end of example 4. Well, it's there if you need it. I think my colorful version is better, but you know, that is what it is. All right, so this text here basically talks about special case products, difference of squares, and perfect square trinomials. So a difference of squares, in this particular case, notice how we have a 2x plus 3 and a 2x minus 3. If we were to FOIL it out, we would get minus 6x and plus 6x in the middle, and therefore would cancel out, and we're just left with 4x squared minus 9. Okay. These binomials, 2x plus 3 and 2x minus 3, they're called conjugates. The conjugate means that they're the exact same except one has a plus and one has a minus. That's all conjugate means. Okay, so keep that in mind for our definition below. And then next, the second special case involves the square of a binomial. So notice if we square 3x plus 7, all right, now first of all, and I know that at least half of you are going to make this mistake over and over and over again. I know this because even my calculus students make this mistake over and over and over again. 3x plus 7 quantity squared is not 9x squared plus 49. You don't distribute the square through like that. You write it 3x plus 7, 3x plus 7. Okay. Well, when you do that and we FOIL it, we end up with 9x squared plus 21x plus 21x plus 49. All right, or in other words, 9x squared plus 42x plus 49. So this particular case is a perfect square binomial, or well, perfect square trinomial, I guess. Okay, perfect square trinomial. Okay, so it's a perfect square trinomial because you're basically saying the same thing twice. So that leads us to these special case products. All three of these are super duper important. They have to be memorized. The first product, the first special case product, is especially important. It has got to be super duper memorized. Sleep on it, right? Like you need to be able to know how to do what's called difference of squares. You need to be able to know how to do this in your sleep. It's very important, 100%. I'm gonna actually just put a star by it. Okay. The number two is also important. It's also important, but it's only really mainly important because it's a time saver. Because if you wanted to, you could FOIL this out and end up getting this particular equation, right? But I'm telling you, in terms of what we're doing, you just go ahead and memorize a plus b quantity squared is a squared plus 2ab plus b squared, and then a minus b squared is a squared minus 2ab plus b. The only difference here is the pluses correspond with one another, and then the minuses correspond with one another. Okay, please, you need to memorize it. It's not abundantly difficult, but it saves a lot of time. Number two saves time. Number one, you have got to know it 100%. Full stop. You have got to know it. Okay. We're just going to go ahead and can we put this on the current page? Yes. Okay, good. All right, so we're just gonna just show the special case products. Nothing extraordinary in terms of the computation here. So notice how well, they're conjugates, right? The first and second terms are the same. 6c and 7d, they're the same. The only thing that's different from them is one is a minus, one is plus. So this must be the difference of squares. So what the difference of squares tells us is all we have to do is square the first term and square the second term and subtract that from the first term. So the first term is 6c. If we square that, it'd be 36c squared. And if we squared the 7d, it would be 49d squared. And then, of course, you just subtract them. And that's what we have here, 36c squared minus 49d squared. B is 5x minus 2 quantity squared. Okay, well, that is this subtraction portion of the perfect square trinomial special case product. All right, all we have to do is do a squared minus 2ab plus b squared. Okay, well, in this particular case, the a is 5x and the b is a negative 2. So you'd say 5x squared, well, that's 25x squared, minus 2 times a times b. So minus 2 times a, so 2 times 5x is 10x, times b, which is 2, so that's 20x, so that's going to be negative 20x, that's what we see here. And then plus b squared, so this negative 4 squared is going to be 4. Right? And then the same procedure can be seen down here in C, and of course, it makes it a little bit more difficult, but these special case products are super duper important. They need to be memorized. Don't stop until you have them memorized. Write them down on an index card, figure it out. Certainly if you just try just a little bit, you can memorize them. But like I said, they have got to be memorized. I promise you. Continuing on in this particular class is going to be difficult if you don't, especially if you don't memorize special case product formula number 1. Okay, so this one is a little bit different, a little bit difficult. I won't say difficult. Now, obviously, difficult for me is different than difficult for you, and that could be said for anything, right? I'm sure that there are many among you that might be good with I don't know, history, might be good with English, whatever. And you might say something is easy, and I'm like, well, what are you talking about? I don't know how to work on a diesel motor. So I say that with a grain of salt. I understand that many of you don't like math. You're in this course because you have to have it. So when I do say this is easy, I don't know. I'll tell you. Easy is relative, isn't it? But instead, what I will say is that this is tedious because I think we can all agree that this is very tedious. And this is a very tedious problem. Right? So let's begin on this tedious problem. Not an easy problem, a tedious problem. So let's first start off by getting rid of our parentheses. So let's get rid of our parentheses. And so I've been asked before, what's the difference between a bracket and a parentheses? Okay. Well, the thing is, in mathematics, they are essentially interchangeable. It's just that if a parentheses is already being used, then we don't use a bracket. I'm sorry, then we don't use another parentheses. We go to a bracket, mainly because it looks better on the eyeballs. Okay, so that's the difference between them, basically. So I'm just going to go ahead and write this with a parentheses instead of a bracket, because I'm going to be getting rid of the parentheses. So x, and then this just turns into plus y plus z. And then my second one is going to be x, and it's going to be minus y minus z. Okay, and then once I'm at this particular point, okay, I'll take it back. On second thought, I got a little carried away, and I was trying to do something that this problem is doing differently. I'm sorry. So what I should have done actually is I noticed that they are conjugates, right? This is x plus y plus z, and this is x minus y plus z. They're a difference of squares. So if anything, what I was talking about earlier about the difference of squares, special case number one, the difference of squares needs to be memorized. It needs to be memorized, and it needs to be able to be noticed when you see it. All right. I got a little carried away, and I didn't notice it right off the bat, but now I notice it as I wrote it out. It has to be noticed because it makes computation so much easier. Okay. So in this particular case, let's go ahead and let's call something be called A and something be called B. Okay, so the A term in this, okay, so again, if we go back to our special case formula, we notice that it's in terms of A's and B's, right? A plus B, A minus B. Well, in this particular case, the X is the A. Can I not write up there? The X is the A. It's A plus B, and this is A minus B. Okay, so my A is the X, and my B is the Y plus Z. So I know that from my special case product formula that this just becomes a squared minus b squared, right? So all I have to do is put a square on them essentially. So I've got x squared minus y plus z squared. Okay, well, luckily for us, we also have a formula for the y plus z squared, don't we? That's the same thing as saying a plus b quantity squared. And on the previous page, we saw that that is a squared plus 2ab, right here, plus 2ab plus b squared. Okay, so we're going to go ahead and fix this up. So we can say, let's go ahead and put a little arrow going this way, like this. So we can say x squared, and then it's going to be minus, well, what is y plus z squared? As we said, it's y squared minus 2ab. So it's going to be minus 2yz plus z squared, right? That's what we got. Our perfect square trinomial formula. And then from here, we can just simply write x squared, and we're going to distribute that negative sign through, so it's going to be minus, let's try that again, one more time, it's going to be minus y squared plus 2yz minus z squared. Okay, so that's a very tedious problem, and it combined the rules that we have seen before. And then the last one we have here is x plus y to the third power. Now let's see, there is a formula for this. Yes. I'm trying to remember. Yeah, I believe there is a formula for this. but I guess for this particular case, we're not going to talk about it, all right? So instead, what we're going to do is we're going to kind of multiply this out. Now, you could, if you wanted to, you could just simply say x plus y, x plus y, x plus y, FOIL, FOIL, FOIL. Yeah, it gets rather tedious really fast, right? Instead, what I would want you to do, well, let's don't mess that up now, is say x plus y squared times x plus y. Okay, do you agree that x plus y quantity squared times x plus y is equal to x plus y quantity cubed, right? Well, actually, let's do this. Let's put the squared first or second. Okay. All right, we're gonna put it second because I feel like it's just easier to do computation, and you'll see here in a minute. All right, so let's do x plus y times, okay, so again, x plus y quantity squared, we know that that is simply going to be x squared plus 2xy, plus 2xy plus y squared. We know that because it's a perfect square trinomial. And then from here, we can do our handy dandy foiling here, like this. Okay, so let's go ahead and do that. Well, I say foiling, distributing. So x times x squared is x cubed. X times 2xy is, excuse me, is plus 2x squared y. X times y is plus xy. Y times x squared is yx squared. Y times 2xy is 2xy squared. And it looks like 2x is done at 2x y squared. And then y times y is y squared plus y. Plus y squared. Okay. And it doesn't look like I can combine any like terms. X squared, y squared, x. I feel like we should. xy, yx squared, xy squared. All right, let me try it. Let me just check my work here, because I feel like we should be able to combine something. So x and x squared is x cubed. That's good. X and 2xy is 2x squared y. That's good. X and y is xy. That's good. Yx squared, 2xy squared, and y squared. Ah, okay, so I knew something was playing tricks on my eyes. Okay, so I knew that we had to combine like terms because just the nature of problems like this. Here's where my eyeballs are were messing me up here. Okay, so we have x squared y here. Okay, now I generally do put them in descending or I guess it'd be ascending off. Well, how about this in alphabetical order? But I didn't here. I put y first. Um, I should have done x squared y. Had I done x squared y, it would have been a lot easier to spot. So there's a good pro tip. I normally do. I don't know why I didn't this time, but I normally do put them in order. So let's go ahead and put these in alphabetical order. Okay. There we go. Now we can proceed to combine like terms. So we've got x cubed. Nothing combines with that, and then we have x squared, and then we have 2x squared y, which we do indeed have that. So it's going to be plus 3 x squared y, and then plus xy, and then plus 2xy squared, and then plus y squared. Okay, so there we go. I used all my terms, and that was so much easier. Sorry about that. Mistakes do happen. Translation. So, if I recall, well, I guess we do touch on this some. But translating text to algebra, it's something that you just it's kind of developed. I mean, it's not. I wouldn't necessarily it's intuitive, but you do once you realize what the statement is saying, you're like, oh, okay. And this is no different. So for instance, this says complete the table. The square of the sum of x and y. So it's basically the square of the sum of x and y. So we have x plus y, the sum of x and y, and then the square of it, which you see down here. All right, this is saying, what is this saying? It's saying x squared plus y squared, right? Or in other words, the sum of the squares of x and y. The third one here, English form, the square of the product of 3 and x. So what happens is it's saying the square of the product. So the product of 3 and x is 3 times x, and then the square of it, well, that's 3x quantity squared. That's what we see here. Right? That concludes this section.